everybody. My name is Callan Bentley. I teach geology at Piedmont, Virginia Community College, and I'm currently in Alaska on Resurrection Bay at the side of the Resurrection Peninsula. And here behind me you can see some really spectacular examples of a primary volcanic structure. All right, so this is a structure that is produced when a volcano erupts under certain circumstances. And the circumstances under which you get these lumpy shapes is you erupt your volcano underwater. All right, so this is evidence of submarine volcanic eruption, and it's called a pillow basalt. This outcrop is spectacular because you can see why it gets that name. It looks like a big pile of pillows. But what this is where lava is getting squished out into the water, and then the outside instantly chills and solidifies, but the inside of the pillow is still a hot, gooey mess. All right? And so when you see these things in cross-section, they'll tend to have an obsidian crust to them and a series of radial fractures pointing in towards the middle of the pillow. And then the middle will be a classic basalt. Sometimes you'll even get a ring of vesicles going around the outside, but a few inches in. So this is evidence of submarine volcanic eruption of mafic lava, and we would interpret this as potentially being produced at an oceanic ridge system. Making these pillow basalts. So this is evidence of basically an old piece of an oceanic plate, maybe the Pacific plate or the Farallon plate, or there's another proposed ancient plate called the Kula plate, which might have been brought into collision with Alaska due to subduction a long time ago. So here we are at Cape Resurrection, which is the very tip of the Resurrection Peninsula, poking south into the Pacific Ocean. And here we've got plenty of these amazing examples of pillow basalts just lining the cliffs. And then here they're being utilized by seabirds. So black-legged kittiwakes, common murres, horned puffins. They're utilizing these slight protuberances to build their nests on. So we'll get up closer and show you how the birds are utilizing those pillows, and also how the bird's excrement ends up staining the pillows and bringing them out into more obvious relief. Okay, right. So all these pillow basalts, so many, they need to be inflated with lava from somewhere. And that lava is ultimately being derived from our planet's mantle. Now, the planet's mantle is not made out of basalt. It's made out of a rock called peridotite. But peridotite is dominated by the mineral olivine, which only melts at the very, very highest temperatures. So when the mantle gets a chance to melt, basically it melts out lots of other stuff. All right, the easier to melt minerals go into the liquid phase, and the olivine tends to stay behind as a solid residue in the mantle. So what ends up leaving the mantle is the basalt. So this is like an extract of the mantle. You could say it's like a distillation of the mantle. And it moves up through a plumbing system till it reaches the seafloor. And then what we're looking at here is some of that volcanic plumbing, all right? Behind me is a sheeted dike complex. And so each of the vertical stripes of basalt that you see making up this cliff, each of them is a spot where the oceanic lithosphere cracked, and then basaltic lava welled up along that crack and sealed the crack shut, and then it cracked again, and more lava welled up along that crack and sealed it shut, and then it cracked again, and more lava welled up along the crack and sealed it shut, and that happened over and over and over and over. And that, my friends, is how you grow an ocean basin. One crack at a time, one dike of basalt filling in the gap between two plates at a time. So this is how the oceanic crust is constructed, how the oceanic lithosphere is born. Transverse to the overall orientation of the sheeted dikes, you can see some rough and crude columnar jointing. So that's a shrinkage structure that forms as fresh, hot rock cools and contracts a bit. We're often used to seeing cooling columns in a vertical orientation due to subaerial lava flows. But here we've got a different situation, which is these originally vertical cracks, and they're losing their heat out the sides. So the columns form perpendicular to the overall dike orientation. So this is the signature of a divergent plate boundary, all right? No continental crust anywhere in the scene here, but just repeated episodes of cracking and sealing of the oceanic lithosphere. So we're looking here at some of the sort of deep anatomy of the oceanic lithosphere, but it's telling us about the birth of that plate. When we head over to the southern tip of Fox Island across from the Resurrection Peninsula, we see something different. And what we have here are sedimentary rocks, and these sedimentary rocks are of two kinds. The sort of light-colored blocky layers you see there are a dirty sandstone called greywacke. And then in between those are thinner layers that split into little black flaky bits, and those are a rock called shale. The greywacke was deposited originally as sand. The shale was deposited originally as mud. And so mud particles and sand particles are different sizes. They represent different energy levels of deposition. The mud is deposited only when the water is very, very calm and not moving around very much. But the sand is made out of bigger pieces, and it takes a more powerful current to move those pieces. So that is evidence of underwater landslides called turbidity currents that avalanche down off the slope of some continent, probably North America, into the deep ocean of the Pacific a long time ago. These strata are late Cretaceous in age, and these turbidity currents would have looked like an avalanche of snow that you might see coming off a mountainside at a ski resort, except it would be dark colored with suspended sand and mud. As the current slowed down, the sand drops out first, the mud stays suspended in the water column for a little while, but eventually it too settles out. So these are spectacular examples of rock units that we call turbidites, all right? Strata that were deposited by turbidity currents, and they were laid down on the floor of the Pacific Ocean something like 80 million years ago. And the reason that they're not now and they're not horizontal anymore is that they got scraped off the subducted plate as it went down the hatch. So most of this seafloor sediment probably got mixed into the mantle, but a lot of it got scraped off and sort of packed on to the southern edge of Alaska. So when we put these turbidity current deposits together with the pillow basalts and the sheeted dike complex that fed those pillow basalts, we have most of the pieces we need to call this an ophiolite suite. All right? Ophiolite comes from the Greek word for snake rock, and that describes the greenish scaly texture we see in some of the basaltic rocks. But in its fullest definition, it includes these deep water sediments as well.